everyone this was very kind invitation to present this year. And apologies to the other participants for not attending many of their talks. This is the first time in my career I'm attending a conference partially. Yeah. So let's start with this. So I'll talk about this, there's some kind of bootstrap equations from using conformal integrals based on this three papers where we, with my student Paul, who has now graduated, we worked out various aspects of conformal integrals.
Koushik, is that mic one?
Yeah. Yes.
Okay. Can you speak closer to the phone? Okay.
Yes. But I should be audible otherwise.
Yeah.
Yeah. So let's start with this. This is the rough plan of the talk. So I'll start with some rather inexact description of the stuff that we are going to talk about. Then I'll talk about configuration space and representation. I'll introduce all these notions. So I'll find out representations of the conformal group and motivate why. On something called a configuration space of n points on RT, we'll be talking about Euclidean articulate theories. Then we talk about correlation functions in conformal field theory and representations that we get from here. Then write conformal integrals which appear in the correlation functions as a so-called GKZ system. And the conformal integral then we read it as what's called a GG system and use it in the bootstrap equation before I go through. And like last year, this is I'll talk only about cons here since the pros are all here. So, so let's start with a very inexact description of what we're going to talk about. So this is our desiderata that let phi be a field or a manifold which I take to be RT, but sometimes I'll just write as M. And we say that it has a conformal rate of scaling dimension delta if it transforms like this and descales. So if the X, the coordinate in RT changes by a non-zero real number lambda, then the field transforms as lambda to the coordinate. Delta is called the conformal weight of scaling dimension. These fields in this conformal field theory are taken to form a ring. Well, basically that means that if we define a product of fields, a product of two such fields at two different points, and it will be given by an expression like this, where C's are constants. This is the distance between the 2 points here, with the scaling dimensions of these two fields and as well as this, and this last one is something that everyone knows. And these are called OPE constants. And the question is that we want to sort of address is how far can one restrict the CFT data, which essentially means the domain of definition of these deltas and the OP constants without considering specific models, their nuances and all. So that's a basic desiderator that we have, the domain of delta and values of C. To address these questions, one studies correlation functions, which are the expectation values of products of these fields. Where I have written this bold delta is an n-tuple of conformal weights of these fields, and X is an n-tuple of coordinates in RT to the power n. So I have n points. Yes, the n-point correlation function. And under a scaling of the coordinates, this is what happens. The correlation function scales with the scaling dimensions of the fields. It's basically what will happen. And this tells me that now we make a jump that this distribution, which is a correlation function, furnishes a representation of the conformal group on RT. Sorry,
I thought you got three scale points but the same. To really get that scaling mode, all the lambdas need to be the same.
Yeah, this is right. Yeah. Thank you. So then what one does is correlation functions remain unchanged under simultaneous permutations of fields. That's basically by changing the X size and delta is together. That's more or less the spirit. There are different ways of representing the or motivating the bootstrap, but this is one of the way of basically writing them. So as an example, in the 4-point functions, we have this. The 4-point correlation function has 4 fits with 4 deltas and 4 different x's. And this one I have computed 1, 2, and 4 here between these two. Once I do that, one has the correlation functions 1, 2, 3, 4 here, and 1, 2, 3, and also these two come closer, and so on and so forth. And there's a field that runs in between, which is summed over. That's the model is the structure of the bootstrap equation. Now it turns out that we cannot really determine the full domain of delta or either the OP coefficients. We shall have to content ourselves by trying to find bounds on deltas. That's what it is. Is lower our ambitions little bit. So with this very inexact introduction, let me over to the course of what action that we'll take. So I'll formulate the conformal group on a Euclidean space in terms of a Clifford group, which falls in the mathematical subject called geometric algebra. And I'll try to in fact, I try to argue that this is indispensable in the kind of computations that I'm doing. It's not just for to do some fancy maths that we are introducing on this. Then the next thing is we said that so we'll not talk about fields much. We'll talk about correlation functions only, and we already said that we'll talk about so these correlation functions are representations of the conformal group. So we look for representations in the configuration space of points on RT. That's a topological consideration. And then using this to, I'll be expressing the correlation functions as solutions of what is called a Chickasaw system, which falls in the subject of algebraic toric geometry. So I'll have to introduce these things. This is some technicalities, but unfortunately I have to introduce all of them. So with this, let's start with the description of the conformal group. So let's start with, so as I said, aim is always RT for me, whether I write it as aim or RT. And so start with RT with a quadratic form of this kind, which is, so it has P plus and Q minus signs here. This is a quadratic form. This also gives the the inner product of x's as well as the norm. And the total dimension D is P plus Q here. We'll soon restrict to P0, so Q is 0. So, but this what I'm talking about in the next 3-4 slides is actually valid for general PP. Now, conformal transformations in RT are angle preserving transformations of RT to itself. That's the definition of conformal transformation. And so the way to use it is, so I start from M. I first take a map. So this basically wants to compactify the manifold RT by adjoining a cone at infinity to have good well-behaved stuff, functions on them. So I start with RT, take this map to map it into this space, M cross R with coordinates X. X is the coordinate of M, and these are two real lines. So U and V are two real numbers. So embed this using this map to M such. The image of this M inside this M dot, this image of this I, this is an injective map, has in it a cone given by this. This is the conformal compactification of M, which is homeomorphic also to SP plus SQ from the previous slide. The way to do effect conformal transformations is you start so M dot is M plus R. You take an orthogonal transformation. So T is an orthogonal transformation of this space. So make orthogonal transformation, bring this back on the C, then take this map back. This is a projective map. You have X V, so X by V, where V is not equal to 0. U is already 1 by this. So first start from M, map by I, do the orthogonal transformation here, take it back. So I T pi, this is the conformal set of conformal transformations on M. So this is the description of the conformal transformations here. There's a theorem started, the first was by Liouville in 1850 and then generalized by Hantjes in 37, which says that the only angle preserving maps of RT or D greater than 2 are sphere preserving maps or Mobius transformations on M. M is RT. And that's the conformal group of M. That's the only angle preserving this theorem that exists. The component that's connected to identity transforms under this group. So for any x in M RT, it can be translated by a vector in M, orthogonal transformation sitting in SO PQ, the orthogonal one. You can scale it by a real non-zero real number, a positive real number here. And there's another which is called a special conformal transformation, which is first take inverse of x in some sense, then translate it, take another inverse for any A in M. I'm going to explain what inverse means. For example, for R2, when these two, the Mobius group is SL2C that we know. Now, I'm going to write, for some reason, this whole thing as a Mobius transformation, and my job is slightly simpler due to the talk of Krishnendu yesterday, where he introduced quaternions. This is going to be a quaternions for 4 dimension. This is the for D dimension. This is slight generalization of quaternions in terms of clifford diagrams. So let me. So this is the objective express conformal transformations and Mobius transformations. So AB plus AX plus B by CX plus D kind of stuff. So let me just, in the 3-4 slides, introduce the notations and terminology. So what is a Clifford algebra? Clifford algebra, which I denote CL by CL PQ for the signature of the quadratic form that is started with. So for a D-dimensional vector space phi, I take it to be spanned by an orthogonal basis of vectors E nu, orthogonal with an inner product defined on that. So this is the orthogonality condition. And let Q, the same Q that I wrote earlier, with a bilinear quadratic form. So E mu square is given by this quadratic form. Now this again the same thing as I wrote earlier. A Clifford algebra is made up of tensors, which essentially means multiplying E mu's together, one after another, constituted from the E mu's, satisfying this condition. This also we have seen in the, this is nothing but gamma matrix algebra. So this basically has a kind of an anti-commutative tension kind of a relation. Theta is the space-time metric, the flat space-time metric, of course. And the dimension is easy to count, it's 2 to the power t. That we all know from gamma matrix algebras. 4 dimension, but is still a relation. So that means a generic element in a Clifford algebra is written, which I write as chi, is written like this. So the first one is chi0 E0. I've taken E0 to be equal to 1. And the rest is like a sum like this. So for example, the next term will be E nu, chi nu, E nu. Then the one after will be chi nu 1, nu 2, E nu 1, nu 2, and so on and so forth. So I have k number of such E's, and k is summed from 1 to d. Since I have d number of vectors, doesn't go beyond d. Okay. So this is what I got like within course sentences. Now there are 3 involutions in this Clifford algebra. One is this is called sometimes called a reflection. This goes by various names in literature. So I'll call it a reflection. It reflects the E mu's by changing the sign. So that means the row of mu1 to E mu1 to mu k is only given by a minus 1 to the power k of the same thing. Tau is called transpose. It essentially means if I have a tensor of this, I just reverse the order of them. So mu1 to mu k becomes mu k minus 1 to mu1. So that's a transpose. And of course, for a single E mu, it's same. Using this, one defines a conjugation in the Clifford algebra called a chi bar. Starting from this chi, I define a chi bar, which is first reflect and then transpose it. So, for example, in the special case, and this is going to be what's going to be useful for us, E nu bar is minus E nu. This is precisely the bar on quaternions that Krishna described yesterday. this is kind of more general here. The norm squared of an element chi is given by this half of chi bar plus chi bar chi. It's a non-commutative, so I have to write both. And one defines a trace of chi as a chi 0. This is that's the trace of chi. Others will be traces that we check. So in the quaternary case, the other so there will be four such you can use. One is identity, the other three are three Pauli matrices, clearly the trace of other such. So now I write a vector in Rd in terms of a Clifford algebra. So consider Clifford algebra d minus 1 now. So now I'm going to Rd. So Q is 0 for me. I take D. So in the PQ, I take P as d minus 1 and Q is 0. And I call it Clifford d minus 1. I can now write exactly as in the quaternary case, but if it's more E's now. A vector in Rd is written as the zeroth component comes with E0, first component comes with E1, and so on and so forth up to d minus 1. So this is the vector in Rd. I've now written it as an element in the Clifford algebra. And now one can just check explicitly that x dot x out of this using the dot of e's that we talked about is nothing but the quadratic form, it's the law. Now comes the inverse of our x. I used this notation earlier. This inverse. So this inverse is x bar divided by the norm square for vectors for which the norm is non-zero, and these are called invertible elements if the norm is non-zero, and the trace is clearly like in the previous case, that's half of x plus x bar. That's essentially because for x plus x bar, I basically have these are bars. The bars basically we do minus signs, everything will cancel, only this will.
So what is small x bar? Second condition.
This.
That's the map, right?
No, this is the definition of a bar, the third involution in the Clifford algebra, which is given by this one.
Okay, so if you take d minus 1, then that will reduce.
For these guys, is very simple. It's basically the E bar is minus of T. So x bar will be x0 minus x1 Q1 and all will be minus 1. So that when I add them, this will drop off only x0 and x. So that's the trace.
So which coordinate we associate with which element is still arbitrary?
Yeah. It's a permutation. So that's why actually I didn't go to write Pauli matrices. These are the ordering in mu is also arbitrary, ordering in x is also arbitrary. So just take whatever you. Right. So I think this is the last slide on this. So now you define, so as I said, so there is some elements called invertible elements if the norm is non-zero. So I denote by the star the multiplicative subgroup of invertible vectors. Now I can multiply clearly. I can multiply these vectors. X dot x makes sense. So take the multiplicative subgroup of invertible vectors, and that's defines a Clifford group out of that. So Clifford group gamma D, this is called gamma D. This is of course subset of the CLD minus 1. Are all those elements in the invertible multiplicative subgroup such that for an x, take any x in Rd, then rho is the reflection. Q inverse also belongs to Rd. That's a subgroup of this kind. Now, this is often called a Velen group after Velen. So now, taking the Velen group, one write down matrices. So this is a 2 by 2 matrix. A, B, C, D are quaternary now, valued in gamma D, this Velen group with of course 0 added. And it satisfies these conditions. A, then the transpose of B and C transpose of D are in Rd. And there's this condition. This generalizes the AD minus BC of SI to 1. So A tau D minus B tau C is equal to 1. So this form, the Velen group, Well, so sometimes this is called the Belen group, sometimes this is called the Belen group, sometimes this is called the Clifford group, whatever. So we know what we are talking about. So I have a 2 by 2 matrix of quaternions. This is so SL2 on gamma D. So these are valued in gamma D essentially. So this is SL2 on gamma D. This is the double cover of the Mobius group in D dimensions. Examples, and D equal to 1, this reduces to SL2R. In D equal to 2, it reduces to SL2C. In D equal to 4, it reduces to SL2 of quaternions. That Krishna we talked about yesterday.
So the double cover of SL2C is SL2C.
No, so
Yeah, I'm confused. Are you saying this SL2 gamma D is SL2C?
SL2 gamma 2 D equal to 2 is SL2C.
Oh, sorry, I thought that was.
That's the obvious group in 2 dimensions.
Yeah, so what?
There's the global A Z plus B by Z plus B.
Yeah, I thought that was SL2C and the Mobius group. And not the double cover.
Well, that's the SL2C, which is the double cover of the rotation. Yeah.
Yeah,
Let's put it that way.
it's double cover.
Yeah, so in some sense, probably I should write a double cover of the conformal group in terms of the orthogonal transformations. Yeah, that's right. Yeah. Sorry for this. Yeah, this is double cover of the orthogonal group that I talked about. Okay, so after this torture, now things are simpler. Under this Belen group that I talked about, this is what happens. X is a vector in RT, but now I have written as a quaternion, and it Mobius transformation is this. Ax plus b, Cx plus d inverse. Everything now is defined in terms of quaternions. This looks very much like the usual two-dimensional complex Mobius transformation. Xij, which is xi minus xj, transforms like this. So there's a tau here, xij here, and there's no tau here. This is Cxi plus.
How was the contribution?
Tau was a transpose. Conjugation was bar. Right. Now, I'll come back to this once again, but let me stress that the whole reason of doing this exercise, writing it in terms of Clifford and all, was to write it in this Mobius form, such that Xij transforms with powers indices -1 here, like the two-dimensional case. This will turn out to be very important for whatever I'm going to say. And without writing it as a in terms of this Clifford, I couldn't have guessed this. We know how to write down the conformal transformation, but I wouldn't have been able to write this directly as a Mobius kind of thing with the powers 1 here. So I'll come back to this again. Now, okay, is it take the mod square of xij. So xij mod is x bar x. Everyone sees that this is what happens. The tau goes away in the mod. The measure of this is the usual lyric measure that we talk about in d-dimensional, so in RT, that transforms like this, Cx plus d to the power -2d. We'll define another quantity, another another Clifford element, chi, which is chi ij, chi ik inverse, chi xij, xik inverse, xklj, this, everybody will identify this as a cross ratio, written in the quaternion form now. And this also transforms like this, and their mod square is an invariant. So mod of chi is essentially the cross ratio for us. So these are the transformations of all the quantities that we need for our calculations under the conformal transformation written in terms of Clifford element. So with that, so now we want to write the correlation function, which we said will try to interpret as an representation. So let me just recall what the representation means here. So representation of any group G actually is given by an action of G on a manifold M. That essentially means that given a group G, I take an element from there, take this order pair G and M, and I write another. This is the rule which takes a G from the group and X from the M and gives me another element in M. So that's Gx. That's the action of the group on the manifold, and that gives a representation. So now if so now what one wants to do, this is super the geometric, it's a manifold. For example, if it's a Lie group, as this is our case, and AM is the group itself because the Lie group is a manifold by definition. So then this gives me the adjoint representation. So the standard adjoint representation, but it can be other things. So now one wants to lift this geometric action on the manifold to some kind of good function that one has to specify depending on the context. So to lift the action of the group on the manifold to good functions on the manifold, which will be equivariant or covariant under this group. So this is what happens. So you take M as a function that takes from M to some domain D depending on the context. Now, so if you this is the action of the group on the manifold G. So this takes X to Gx. So X to Gx by F. And so then first operate by G. So this is that part. Then by F, go here. Here you take the function first. Then in the domain D, you take another mapping, which is RG. And if they're related by this with some possible factor of alpha G here, then we and with this condition that RG G prime is equal to RG into RG prime, we say that RG is a representation. If this function space, this domain is M itself, then we have matrix representations, like in the SU2, SU3 matrix representation that we have. So now I want to lift this. We have talked about the action of the conformal group on RD. I want to lift it to some functions. So I have to look specify what kind of functions I'm talking about. We are talking about endpoints here in G. So I have an endpoint correlation function. So G is a distribution which is depends on n such coordinates. We can consider either a tensor products of representations of G on the manifold itself, which I will not do, or in classical mechanics, we have all studied things like a configuration space. So I have some kind of manifold and there are endpoints that go down to the manifold, right? So the space of n points moving in the manifold, the usual configuration space of points. Typically, it's a very complicated base, but on the other hand, there are some results known which will be useful. So I look for representations of the conformal group whose action we have already talked about on the geometric space, and we look for representations of G on the configuration space of n point marked points on n. So I have a manifold and I have a bunch of marked points on them. So this is RD. So that essentially means that, for example, what will be this manifold? Oh, sorry, I should have gone there. So what is this configuration space? The first point, mark it as 1, can go around, it can go around in the whole space. So that's RT. The second one can go around everywhere, and now I don't allow it to coalesce. So that essentially means it has to be RT minus the first point, and so on and so on. And clearly, this is a very complicated object. So it's a very badly singular space.
Yeah, I have one. I mean, the way you're defining, representation, with the help of a manifold, is that always necessary, or is it just a test space again?
You see,
I mean,
I'm talking about this. This will be always no. This can be
M is a vector space.
This M is typically a topology. So you can do whatever you want. But I'm taking a manifold because in this context I will talk about it. And typically in Lie groups we actually take them. But for example, if you're a discrete group, you will take it as something else. Yeah, generally you define. So if you wanted to define the most general way of representations is the action of group on a topological space. You start from there. Yeah, like permutation group is not only on the manifold. It's on the subset. Yeah. So for the configuration space, so one has to actually make some sense out of the singular spaces. One has to take something called models. the one I take away is the Fulton, is what is called a Fulton-McPherson completion of this model space. So here's a kind of non-rigorous idea that, so as I said, so you take non-coalescing points, so you have n distinct points in M, group them as they collide, so you can classify them, that so two of them.
So, so you are demanding non-coalescing points to define the inverse. That
No. So, you see, non-coalescing to avoid some singular points first. The coalescing points will be singular points, but we are going to, the completion will introduce them back. So this is like so it's exactly equivalent to writing in a 4-point polymeter this etc. But then you add this. This is the completion of the model space. That extra singular or a simpler example is the 1-point compactification of the complex plane to a sphere, if you want. So you basically add a singular point, call it a good point. So that's what they do. So there's a classification of points depending on how many of, for example, 2 points can come and collide if and only if the velocities are equal, right? So now if the velocities are equal, we look at acceleration of those and then try to separate, distinguish them. If even the accelerations are the same, go to the higher derivative. This is basically what the way to classify things, and then group them as they collide according to velocity acceleration. This is called what we mathematically called a stratification, and then include all such configurations.
so is like doing the conventional that we talk about the T expansion. So this where you were kind of putting in that.
That's basically why I went to this description first. This is like in field theory we talk about like separating. This is point splitting, separating things. Here they are talking about colliding. It refers of that essentially. Yeah, but that's basically, if you go through this literature, you will see all these binary trees now.
And then why did you call it a model? Is there an ambiguity?
There are various ways of see. We are talking about a singular space. You want to make it non-singular somehow. There are different ways of doing that. So there, for example, something called wonderful compactification, which by Koushik and people, which uses more of group theoretic stuff. So yeah, so there are various kinds of models. So this is this is very general and works beyond manifolds. This works actually on varieties. So right, so this is the Fulton-McPherson. So this is my configuration space. So C n m is m to the power n, of course, n number of points. Where I have taken out those points which pairwise coalesce. Then this is this Fulton-McPherson is given by this embedding, and this is basically what we are going to use. So you embed this in this big space, m to the power n, the usual one, added to the n number of points. Then there's a d minus 1 dimensional sphere, and then this n choose two number of them, and this is the interval, which again is n choose 3 number of them, and the coordinates are this. So of course these are the x1 to xn's for m to the n. These are given by, this is a definition, vij's and xij by mod xij. And clearly these are spheres because the mod is 1. This gives you spheres. And there's this ratio, xij by xik. So that it's called aij, and clearly this goes from 0 to infinity. These are mods, so it is positive. And these are these guys. So that means that so as I said, I'm looking for functions, good functions on the configuration space. It means that functions that we write down are going to be functions of x, v, and a. From this argument, and in this space. And we said GNs are representations of the conformal group. So I'll take GNs as functions of this. And if you remember, I have actually already listed the transformation of all these quantities under the conformal. So now I'll be able to use it. There's more. Translation invariance forbids just x size, so only differences will occur. Rotation will take away the x size as it is, only mods will occur. And now from now on I'll talk about scalar fields. For scalars, there will be no Vij as well. Vij's will come for speeds, high speeds. And of course, there will be Aij. That's there. So this is the transformation under the conformal group. So under conformal group, you write as G transforms under this action of X now as this, and as Connor pointed out earlier, in the same set of singularities. And this gives me this RG, the representation of the conformal group on these functions. So I'm looking for this. So basically, this is how I want to evaluate my Green's function, correlation functions. Now, covariance under the conformal transform, everyone knows, fixes the 2-point correlation function directly to this. That's actually very easy to see from here. That if I have only 2 points and it's same C and D, there's not much I can do. So it fixes both the deltas to be equal. The 3-point function is also fixed like this, standard formula. These are the OP constants, and these are the powers. So everyone knows this. 1, 2 comes with 1, 2 by and so on. So I'll spend time on that, and I'll go directly to the higher points. So now, at higher points, the higher point correlation functions are obtained by parsing this expectation value that I started with the projectors inside. You just pass them by inserting projectors, so that you can write it as a 3-point correlation. And the projector is this. So I have a phi delta here, kit, phi delta bra here, and this factor. If you work out one of the integrals, this will be basically phi and its shadow, or the shadow and the phi, depending on which one you integrate. I'm not integrated either. I'll keep everything general. You can check using this that if you write pi square, pi compose pi, and when you compose this with another pi, you have a expectation value of 2 of the fields. You insert this 2-point correlation function there, and you can check that this is exactly pi square is equal to pi. So there's projection operator, and with this n. That's just easy to check equations.
So the exponent of the denominator is fixed by the.
This is conformal invariant. Yeah, you don't want any. So projector. This is p square equal to p, so you don't want dimension there. Right. So now this. So this is basically what one does. You put in a projector here, break it. So then this breaks into 3 points because this introduces one extra point here. So 2 here, 1 from here. That makes it a 3-point function. So yes. So I have a 3-point function, and then I have the rest. For the rest, I have to again insert a pi somewhere, and this goes on. And now I have to. So this is and so I have to now basically plug in the 3-point function here and integrate. So here's the expression for the example for the 4-point function. So the 4-point function. So I'll have basically up to 4 here. So I have 2 3-point functions coming up.
So what is this 1 by into the delta 1 by n normalization?
This is a normalization that will happen. Yeah. Right. So yeah. So using 2 G3s, G3s are completely fixed. Just plug this in the formula and then start doing the integrals. So once you do that, you have these expressions. So the first expression is the usual one. So I have 2 OP constants coming from 2 G3s, and then also sitting there. Then I have these factors, sometimes called the leg factors, I guess. X1, 2, and X3, 4 with certain weights here. And this is sum of a lambda delta that has come up. Coming, so this is a projector, and I have summed over the projectors. And there's this quantity I. There's a number here. This is 4 for n, and there are 4 numbers here, and of course x 4 coordinates. Then I changed exchange 2 4. So lambda delta 2 delta 4, and simultaneously x2 x4, and this gives me this. So this is what we call S, and this is the T channel in this notation. And the bootstrap equation that we talked about is this. The correlation functions in the 2 channels after an exchange of 2 and 4 points is this. And we have defined this new quantity. This is the general definition. So I had 4 here and 4 numbers here, 4 coordinates here. This is the general one. So I have an n tuple of numbers here. Mu1 to so this is sorry, this is a typo. This will be n and this is the mu n.
Can you just go back to the for one function representation that you had, I think one slide earlier? Yeah, this appears as if, I mean, if I'm not misunderstanding something, that you can exactly evaluate the 4.4.
I mean, you can evaluate the integral, and that's what you get. But in terms of this integral,
Yeah.
so far,
No, but this equation has lots of unknown data, right?
which equation? Which equation?
But okay, there was this equation you showed for when things were crossing like this, which you call like S,
Yeah.
right?
Yeah.
How do you fix those things?
As I said, so first I evaluate this and then exchange 2 and 4. I have to put somewhere else also. Yeah, they can do this. So exchange 2 and 4. So that will be x1, 4 and 2.
No, my question is, how do you restrict, let's say, what these numbers, deltas are and.
Delta 1, 2, 3, 4 are arbitrary so far.
Okay,
And this delta is summed over. And we want bound on that. So that's the question anyway.
Maybe it becomes 8.
But these 4 deltas are so far arbitrary.
Yeah, I
The
understand.
simple parameters in this,
And that's what you're trying to constrict.
yeah, eventually.
No, not.
Not those deltas. Those are external deltas to be supplied. The one inside, which is summed over, is to be. I mean, we are looking for a domain of that.
Okay.
Right. So this is.
And just to understand, I mean, so far, there has nothing been used about 3-4, right? I mean, till this point.
So, yeah, that's it.
And just to completely understand.
So I think it's in the next slide or so it will come.
And just to completely understand, there's a single delta type.
Okay. So yeah, that's it. As Koushik mentioned, so far this is a standard calculation. I mean, putting in a projector and writing things. But this is a bad typo here. Sorry, this will be n. This will be n. This is a mu n tuple, and there will be n number of projects. So right, and now 3/4 comes in. So now I have to evaluate. Basically, I have to evaluate an integral of this kind. Rest is gone. So this is what is right. So interestingly, what happens is now you take this integral. I don't want to evaluate integrals. I want to write differential equations for it. As is kind of common in many situations. So differentiate with respect to the xi's within the integral. So take 2 derivatives, xi and xj derivatives. You can now check that this can be written as this, where these are now the default stuff. It's very difficult to write this in a better form. Actually, we have tried many various versions using normal Laplace, etc. This is the best way of writing it. And this has come directly from the 2-dimensional case. In the 2-dimensional case, you don't need to put a mod. You just take meromorphic functions here, z minus z1, z minus up to z minus zn, etc. And this is exactly like the Christopher Schwarz map kind of a calculation. But yeah, so it's a generalization. And there's this beautiful identity that also generalizes from the 2-dimensional case or real cases. So you see, when you differentiate with respect to say xi, you will increase this factor by 1. So there will be a 1 factor in the denominator. With j, there will be 1 factor in the denominator like this. And then you massage it using this, you will get this. This is 2 steps. So that's kind of interesting. That is trivial looking identity actually is this. Now we said that now we see so if sum of mu is d, this mu's. If the sum of d, if you remember, I said that this d transforms as mod c x plus d to the power minus 2d. And if the sum of d, then this cancels, and this is conformal. What you see is that so the transformation in x's cancel, only the transformations in xi's survive, and it gives this under the conformal Mobius transformation.
I'm a little bit confused because for the 4-point the composition, it indeed is a single integral, but for endpoints, we're going to have a bunch of integrals, not just a single integral, right? Because we will iterate the projector and we'll integrate many times. So this
Yeah.
is,
So this is the, this is the notation. So this is for 4 points I made this.
sure,
With 5 points restriction, I have integrals after integrals, but it will be more integrals on this conformality. So that it's a very complicated stuff, but I can do this calculation in care. So I basically, yeah, that's the motivation so far. Yeah. Right. So now this is also a covariant expression under the Mobius, and this is now with this condition is called a this is what we call a conformal integral. Actually, we call it a conformal integral in this context, but this I think was conformal integral was first dealt with by semantic, so long time. Well, so this is also, so this means that under the Velen group, this also transforms covariantly. So I mu like G is also a representation of the conformal group. So I mu is also a function of this mod Xij's and Aij's, like in the previous case. We are talking about scalars here. But now there's slight twist in this problem that this I, as we know, contains conformal invariance. The chi's, mod chi is that A. We can have that. So now see, mod chi can be written as the product of two AIs. So I can also think of this I as a function of mod X's and mod chi's. So cross ratios and the separation between coordinates. So I will take that. And now comes the second point why this is important. This is something we had. And I mentioned that it's very important that this transform like with one indices 1 minus 1 here. So now collect the exponent of Cxi plus D in this matrix. So, for example, in the transformation of Xij, so here it will be 1. I just ignore the minus sign, so it's 1 for Xi, 1 for Xj. Only. Rest as 0. And collect them in a matrix, it will look like this. So this is the exponent in the transformation of Jk when exponential transformation of Xi in the Xjk. And I'll denote the null vectors of this. This is a matrix by this curly L. This is the null vectors on it. So as an example, for n equal to 4, you have 4 points. So you have Xij's 1, 2, 1, 3 up to 3, 4. So in 1, 2, it transforms under 1 and 2. So I have 1 and 1 here, zeros here. 1, 3 transforms under 1 and 3. I have zeros otherwise, and so on and so on. Again, I couldn't have done this, I could have guessed this structure without the three-fold algebra structure. I needed the Mobius transformation to write this, which was obvious in 2 dimensions, but unless I generalized using this three-fold, I couldn't have guessed these numbers. Because the good thing about it is now this along with this, these are the null, so the transpose of this, there are the 2 null vectors. This is a 6 by 4 matrix. So the null, there are 2 null vectors. The transpose of these are the null vectors.
Sorry, I have one question regarding that. I mean, do I understand right? The scale that you have is written as an integral, right? Okay.
Yeah, this is, yeah.
Sorry.
Anyway, that's right.
Yeah. So this integral is the conformal block. Is that right? Or there's some.
Let me comment on this.
I mean, for the 4-point function.
Yeah. So yeah, let me comment on that. So it will be part of this will be the conformal, but there will be some factor which will also contribute to the leg factor. So it's not yet the full, yeah. So this is going to provide me the summand in the conformal law. That's true, but there will be another factor.
And the differential equation that you write. So usually the conformal blocks also satisfy a differential equation, right? So is this differential equation identical to that with that?
It turns out that I can derive
quaternion version of that.
Quaternion version of that, but yeah, as we see, this is much easier to solve because there I don't have. In 4 dimensions, we actually didn't have this. We actually walked out the long way, and without. So as I said, so this is going to take me to the realm of toric geometry, and there are algorithms for solving these problems. Otherwise, you have to actually really massage the equations the hard way to see that after all these are hypergeometric. But on the other hand, now with this very simple thing, I'm going to explain this, but I can write down this matrix and there's some geometric differential equations associated to these guys, which tells me how to solve. That's what I'm going to use. This is the third ingredient that I talked about is the stoichiometric stuff. So,
And just to clarify, so far, when you are discussing all this, are we restricted to a particular dimension?
no, D. Because,
Ah,
because this was a D dimension. That was the whole idea of generalizing this. And it's interesting that in all dimensions, I have this similar structure of the matrices. For 4 points in all dimensions, I have this. But what will change is the, essentially nothing will change. Now, as this is related to Jyotir Moy's question, so I take this as an answer for the I. So I take, I know that there will be an invariant part. This is what is going to contribute directly to the conformal. Where I have defined size as skies are the same, which are like this, and you see, I have L's here. If you look at it, this is how I define L's, the size. So L will always have this structure that certain number of them will be positive one, certain number will be negative one. So for example, here I have 1 in 1, 3 and 2, 4. So 1, 3 and 2, 4 goes up, and 1, 4 and 2, 3 come with minus sign, so they go down. That's the way to write a cross-ratio form. This is of course a chi-ijk's that I got. So start with this matrix, obtain from the transformation, write down the null vectors, you define the cross ratios. Direct. So those are the xi's here. And this invariance, as I wrote, it appears as a summed in the conformal. This will appear there. Only function of cross ratios. And these are conformal invariant real cross ratios. So yeah. So now I plug this back in the equation, in this equation. And there's again still some messaging to do. Here I have chosen betas. You see, this I transforms in this particular fashion. Psi is invariant, so betas will have to take the transformation part. So that means they will be related to the mu's, and the relation is this using this same toric matrix.
Remind me what are the names again, sir?
So mu's come here. So that's the transformation part. So betas will have to take that up. Xi's are this is invariant part. So that's to be called. So basically, these betas are related to the mu's. And this by exactly this, where this A is that same matrix. So there's this relation. Beta ii is 0, xi minus xi doesn't appear. So beta ii is 0 and this symmetry. Now you see, I had n number of mu's, but I have n choose 2 number of betas. I cannot, of course, I will not be able to solve this, but you can prove it as a theorem that this choice of betas is not unique, but and also this is a null vector, so you see, if I add a piece like this, A is a null vector of A, so this also doesn't change this relation. But it can be proven as a theorem that what I'm going to write is in conformal integrals, they do not depend on the choice of betas. They only depend on the means. You can do it, to calculate it also, but you can, this is the case, but you can actually prove it. Now, inserting these ansatz with all these properties in the differential equation, and so in this differential equation, you have 3-4 numbers, E bars sitting here. In the end, you take a trace to get the zeroth component. You get some operator, not particularly nice looking, but has nice properties. So you can prove that the invariant part satisfies this equation, where I have defined thetas as derivatives with respect to the cross ratios. These are basically the Euler differential operators, giving you the scalings. So this is okay. Don't worry much about that. The point is, I can rewrite this as a difference of these 4 index operators with some sum here, when this looks like this. This is an observation that we made. It was not obvious. And then, which is more interesting, is that you see that if I assume that the full I mu, the full conformal integral satisfies this differential equation with delta ij's derivative with respect to xij squares, then this implies that Lij acting on I0 is 0. That in turn implies that Lij, these both of them are 0, so Lij acting on this is 0. So these are sufficient condition for the solution of.
So as Jyotimata was asking.
Yeah.
So, conformal blocks satisfy conformal Casimir equation. So which one of these would correspond to?
Let me comment on this at the end, because I have some guess about it. Yeah. But at the moment, so I have already taken care of the fact this is representation of the conformal. Just one thing by the answers and all. And then I have a differential equation directly for it. So it already has a Casimir, that much is there. But let me comment on this.
Another question. Is it fair to say that you are actually just computing a scalar exchange block because it didn't have the numerators in the integral, right? So it's really only a scalar exchange.
Yeah. So I'm
not just saying the external ones, I'm saying even the internal ones.
Yeah, even internal is scalar. But on the other hand, okay, let me just, since you asked this, I thought I'll talk it about later. But I can actually, in principle, I can handle the other speeds by taking derivatives here with respect to x's. The Vij is been found. So at the moment, I'll just concentrate on this. This is a very the simplest case that one can come. That. So now with all these gymnastics, I ended up with this equation. I have to only solve this equation.
Sorry, how did you get this equation?
I'm saying that this was an observation that we made, that first I had this. This Lij, whatever it is, could be written in terms of a 4-index operator. Where is this? Then we observe that solution of this implies this. That Lij on I0 is 0. Sorry, Lij L 4-index on I0 is 0. So each of them is 0, so Lij is 0. Yeah, this is again, this was not obvious. We have to you can in principle guess it from the fact that you already have a toric restriction, but you have to sit down and check this first one. Here. Right. So in the end, I have this, and I have this equation of this equation to be satisfied. I have betas too. So all in all, this is what I have. So these equations can be rewritten as this. So I have A here. This is the Euler operator with respect to x jk square on I mu. This is the scaling of I with the mu cube that appeared in the integral. This is 0. This basically is telling that the scaling is mu's. And this is the second operator here. Written as this because remember, so this basically says that here you take the positive components of L, here you take the negative components of L. So if you go back, here you see 2 of them are positive, 2 of them are negative. So it gives you this form. So these are the equations, and these are called GKZ generalized hypergeometric system, and their solutions are GKZ hypergeometric functions. So now we have mapped the whole problem of the conformal integral to a GKZ problem, which is the solution requirement. So this people. And this is essentially, it tells me that I wrote down formula. This turns out to be the equation exactly the toric beta with Grassmann variety. You can think of this as the hyperplane sections and all, but I'll not get into that. So that's very important. So here's that, okay, this is trivial. How do you time?
Like 30 minutes.
Oh, 30 minutes. So I'll finish it. Okay, so here's an example. So for the 2 point, just to say that this is consistent, this is data okay. The toric matrix is 1 and 1. Because under 1 it transforms as 1. I have only x1, 2 to talk about. Are both under 1 and 2, the indices are 1. These are no kernel. There's no trivial, so does not have a null vector. So that means this equation is not there. I have only this equation to satisfy. This is this equation which is solved with this. So I know this had to happen. Similarly, for n equal to 3, I had 3 things 1, 2, 1, 3, 2, 3, and 1, 2, and 3 to look at. So this was the toric matrix. Again, there's no null vector. I have only the first set of equations, this set of equations. You solve it and you get this. Now 4 point. For 4 point again, I have rewritten the whole thing. This is the toric matrix, and This is the set of null vector, null vectors, and they define this cross ratios once again. This is 1, 3. This is 2, 4. It's 1, 2, 3, 4, and the minus 1 side 1, 4, and 2, 3. Here I have 1, 2, and 3, 4. These are the positive ones, 1, 2, 3, 4, seven ones. Yes. So these are the cross ratios. And then you can actually write down the solution of this. And with the convergence domain, it turns out that I have now two cross ratios. The connected component of there's a discriminant locus here, and which you can evaluate from the toric data. I use Macaulay 2 to do this. You find that this is the convergence domain, this is the discriminant locus, and this is now related to some kind of combinatorics of this, thought of as a set of vectors in a R4 integer, at least Z4, and there's a particular way of so if you write down 6 vectors in essentially in R4, so of course they're not linearly independent. But to write poles out of this, so think of this as the points of a polytope in the 4 dimensions, and triangulate that polytope. So you can actually check again using Macaulay that you have 4 independent regular triangulations, and correspondingly there will be 4 independent linearly independent solutions, and these are the solutions that they look like, and according to Jyotirmoy criteria, they are not very simple. So, but okay, I don't even want you to get look into this part. The important thing is that this is given by a power series in psi 1 and psi 2 cross ratios. So that is it. That also means that there's a convergence domain associated with which is this. It has to be on one side of this curve. So there are 4 such solutions here, psi 1, psi 2, psi 4, and there's a linear combination that you can write down to write the conformal integral. Now you have to determine the constant, of course, you have to put in physical inputs. In our paper, we did put a physical, we actually did a permutation invariant combination, which we don't need in physics, but yeah, it can be done.
Can I ask a question? So if we go back to this infinite series expression, so it's well known that in even space-time dimensions, things are simple and these become simple 2f1s or products, while in generic space-time dimension, this does not happen. Is it easy to see why even space-time dimension is special?
I've not checked that. That depends on the structure of this. But remember that these can be written, okay. Yeah, these 4 can be written as apple here.
Sure, but when space-time is even, like 2, 4, and so on, it should even become simpler and become just 2f1.
That's right. So that depends. In fact, I don't know how general that statement even is, because if one should go beyond these 4 points, it will be the conformality will love each other kind of function.
It's 4 points.
But 4 points, Apple functions has certain properties for certain cases. It can replace the product of F2 ones. So that might be a nuance of that. I'm not sure it's a generic. But I have not checked it. I mean, I have looked into it. But my guess is it's not very generic.
Isn't this the kind of integral that the one in Osborne would call a D function? Where you have 4 points all connected to one central point. You get to
D function.
Yeah. I mean, they have. It's just an integral of dx where you have x minus x1, x minus x2, x minus x3, x minus x.
Yeah.
So I don't think that's what becomes the integral.
This is the that's the conformal integral here. Modulo the time for this person. X minus x1, x minus x2. It's that's what I'm solving for.
Yeah. I don't know. I have trouble seeing that that's going to be into it's different. Wow.
So isn't this the simple formal partial rate for the Faulkner?
It's a partial rate. It's a partial. That's right. It's the standard form of partial.
If you pull out x1 to an x3 then it's
Right.
x1 0, x2 0, x3 0, x0 0.
But yeah.
This is partial. Apart from the link factoring, it's x to the power beta ij that I0 is basically the partial. Yeah, this is the partial. I0 part. right? So now basically if once you plug this in, you get expression for the cheese correlation functions. At least for the 4-point, then as you said, write it down for the 4-point, do the more projections and so on and so forth. You get sums over of this. So they're basically a sum over apples, the functions with parameters in the apple summed over. So that kind of stuff, complicated stuff will happen, and that happens. That's there in the paper, etc. I don't want to get into that. Now, the final thing is that if you now wanted to use this for bootstrap, what happens? And here again, as Antonio already pointed out, that I'm only talking about the very simple case of all scalars, even the internal one is scalar. So I'm just looking into that case, whether this is physical or not. Let's look into that. Interesting thing is that.
So is it a special CFT where spinning exchanges are not present?
So I have to interpret it that. I'm just doing the calculation for that, whatever it takes. And try to see if even in this case, there's a chance that this will try to basically see if this has any chance of giving a bound like this before getting into the more complicated ones. So there's this interesting thing that, as I said, so once you try to write this in terms of series, there's a problem of convergence, and once you try to put them in the bootstrap, you have a sum over the deltas which are unknown, then you have sum over these n's. That creates a lot of problem. And then if you want to multiply this with a cardinal in the which are dependent on the xi's, you have to be very careful of the convergence of xi's and so on and so in the integrations. There are papers where he actually points out cases where the Fubini theorem breaks down and the integration, swapping integrals of sums are complicated. So now, instead of going that way, I now go to another thing. There's something called a GG system. It's called Gauss plus 1 by the discoverers who are Gelfand and Grimes. So probably, it's very interesting. But actually, this probably is called a Gauss Grassmannian because it's Grassmann because, as I said, the toric data is for a Grassmannian variety. And Gauss is because it's related to a Gauss-Bonnet connection sheet. So that connection that one is writing down in the GTL system. But anyway, this invariant part, I0 n only dependent on the cross ratios, can also be written as this integral. I've just lifted it from the paper. You can even prove it in for a given toric data A. So given a toric matrix A that I started with, satisfying this system, this I mu satisfying this system would be written as this with this I0 given by this integral. So these are like Schwinger point splitting integrals. These are Tij's with t to the power stuff, e to the power minus Tij and so on and so forth. And remember, I told you that I mu is independent of the choice of bitters, but this is not. This is only a part of that I mu. Then only the invariant part. Now, in this now, I don't have to worry much about the convergence domains of in the space of cross ratios. I'm writing an integral. It's only when I evaluate an integral of this kind, Euler, it is like a generalized Euler integral as well. And then now I'll be able to integrate over cross ratios. So I can write. So start with this. I can write down the formula for the Mellin transform. I just take a standard Mellin transform for each of the variables that I have. This is for the endpoints. So I multiply with each of these cross ratios with a mu minus 1 along with this, and I can just do this integral. Now, interestingly, and now I'm changing the order of the integrals. Here I had integration over the Tij's. And now I'm changing order of integral, first to the psi integral, then the t integral. And it turns out of a very simple product formula like this. Once you do that psi integral, you more or less see that this there will be factors of in the measure coming up, and the rest of it is nothing but a gamma function in T's. It gives me only a product of gamma functions here. Where I have the beta ij's sitting here, and there's this null vector sitting here with the news. Okay.
Sorry, this I mean new comma beta, is it just a mailing of the?
Yeah, that's right. I just took this and took the mailing of that. Just simply the mailing of that in all the cross sections.
Yes, okay, and then what do you do?
No, I just wrote this formula for the time. And so what I did was, so there was an integral over the TIJs,
Yeah, good.
and now I'm integrating over xi's.
Right.
I'm just swapping the integral. First do the xi integral, then the T integral.
Okay, yeah, that's fine.
That should be fine because now I don't have series to worry about. So I don't the convergence those domains to worry about. But now
So
this,
just to understand,
Yeah.
and for the 4-point function, we give the usual mailing amplitude that.
I should get here. I have the expression for it. You will probably see it better much faster than me. Yeah. But this is what I get as a mailing transform of the invariant part. Now I go back to the 4-point bootstrap equation that is wrote down earlier. There I identify these mu's from the formulas that I wrote down, the integrals. Solve for the betas. In solving for the betas, I have to worry about the OP consistency. So in the S channel where 1 and 2 can come closer, beta 1, 2 had to be put to 0 to have the OP consistency. There, in the T channel, I had to put if beta 1, 4 to 0, 1, 4 could come closer. So with that, I can solve this set of betas except one. I had 6 betas, 4 equations, so I could solve only 4 of them with 2 left. One of in each set is fixed by OP consistency. So I am still leaving the one parameter. So once I plug all this in this case, now plug this in, and so what we'll have is expressions of I0 from this integrals. I'll have I0s and then leg factors. You can multiply leg factors from on both sides as long as this that delta dependent parts are not touched. And basically rewrite the bootstrap equation only in terms of cross sections. That's always possible. So I have done that. And now here I can just multiply by this Mellin thing, cardinal, and do the Mellin integrals. That's what I do. So if I do that, I have this formula. So what C1 to delta, delta 3, 4, and this expression is this 4 gammas. This expression is this 4 or 5 gammas. And here I have actually deleted some common factors which are not dependent on delta.
But so normally, in the mailing amplitude, like, I mean, what for the descendants you need poles. This is exchange diagram, right?
Yeah.
The poles are in the gamma. No.
Yeah.
But usually the recipe is given by map. That's one. Still, you get it 3 of 2, right?
Sorry.
For a scalar exchange, you get a 3 of 2 hypergeometric functions.
I have got some. I didn't even try to sum this up.
This is just the Mellin amplitude of
This is the Mellin amplitude.
diagram. In reality,
Right.
it's just partial. So it just means that it's on the S channel,
This one is channel.
but it's the Mellin amplitude of that formal integral, which is just a contact. From the point of view of the Mellin amplitude,
That's why I was confused before.
but why it's
So the conformal block for a single trace exchange is coming from something. You think that's only double traces.
Yeah, that's.
But I believe this is correct.
So I didn't get the point yet. A question.
I mean, I think the point, so. Very amplitude.
I'm not an expert on Mellin amplitude either, so.
We should have a pole.
Yeah.
I think that's what.
There can these gamma functions will have those.
It's just a different use.
Yeah, but, this kind of, let me just proceed to write down more formulas if you clearer.
Yeah, every other time I've used known amplitudes, the gammas have
delta 1, 2, 3, 4, and I never have delta 1. So that was the
Status right now.
So delta is sitting there. So in the partial, as you said, it's a partial wave thing. So this is some of the delta inputs. And I just wanted to use this to check with this boundary situation can be done. So this is what. So now I put all the external deltas related to Arnold's question. Now I put all the external deltas 1, 2, 3, and 4 be equal. Delta 0. And then this simplifies. So I basically put that in this formula, and it gives me a relation of this expression of this form, where this L is this, R is this. So this is basically reducing that. Equations. Now about bounds. This is a standard stuff, except that let's also point out that I could have actually multiplied with any kernel of Xi1 and Xi2 and integrated over. I just chose to do the Belling simulation. In principle, there's nothing that stops me from multiplying some good factors of Xi1, function of Xi1, Xi2 and integrate. That I could have done. I just chose to stick to the Belling because it's simply simple. Right. So now, see, so this in some sense tells me that I only have one parameter freedom in the determination of C or delta or whatever I want to do. I have a whole one real parameter freedom. That's one interesting thing. And then there'll be now to find if there are bounds. All I have to calculate probably is the ratio of L and R, and if it crosses 1 at some point, there's a chance of having cancellation. Right?
So sorry, very nice question. So you find a bound on the internal delta in terms of delta naught. Right.
Yeah. Right. So point is if this has to be satisfied, some of them has to be positive and some of them from the terms will have to be negative to cancel stuff. So one way of seeing this, and of course one way of seeing this is if this ratio L by R, if it crosses unity, then this might happen. So I can give a bound from there. May not be the best bound, but some bound. And now there are 4 parameters in this thing. One is of course the dimension, then this delta 0. Nu2 is a free parameter in the coming from the Mellin. It's a Mellin index. And beta 1, see that was not determined, and the minus nu1, I can think of this as a single parameter because it always appears in this combination. Whatever it appears. And then varying these parameters, I can try to see what kind of bounds I get, and these are the plots. The first one, I have chosen this. So this is D4, beta 1, 3. I have chosen simply as nu1. So this parameter is 0. Nu2 arbitrarily chosen as 3. And delta is chosen to be this, satisfying beyond the unitary bound. And I see that there are points, and I have now changed delta zeros, the external deltas. And I see that every time there's one point at least where it crosses unity. Similarly, here I have changed the dimensions, keeping fixing the rest. Here I have chosen the delta 0 exactly to be d minus this unitary bound plus 0.3 arbitrarily, and it's always again these things this ratio crosses 1 at some point or the other in this. Interestingly, now here when I change beta, I have fixed the rest. Beta changes from nu1 to nu1 plus stuff. I see that there's not much sensitivity here. It's, apart from this guy, everyone processes it at this point. And similarly for the one when I change nu2 separately, I see that is more or less the same for various points. So it tells me that so this part GG form of it of the conformal integral, it seems to be useful in evaluating the bounds on this. And with this, I will.
It seems that there's some unitarity bounds.
Yeah.
So if you sort of violate them, then do your equations say that you are not crossing this one?
I've not checked that. So then, I mean, in principle, I could have plotted directly against delta. But since there's a unitarity bound, I just chose to plot it beyond that.
But that fact should also come out of these equations, right? Or
Which fact? Unitarity is a separate issue. I have not talked about it. Unitarity has to be separately put in.
But your ability to derive bounds assumes that you are summing these things with positive coefficients. So in a non-unitary theory, you wouldn't be able to use these laws to guarantee.
Non-unitary will be slightly different, and also one has to look into it. But here the point was that these are real numbers, C's. So this is always a positive number. That is the standard theory. So with this, let me come to the conclusion. So let me summarize basically. And so basically we said that the conformal correlation functions are representations of the conformal group. That was the beginning point. And conformal group in d dimensions, I note in terms of Clifford algebras, and I try to motivate that without rewriting it in this form, I couldn't have guessed something like a toric matrix later on, and also couldn't have written down the differential equation for the conformal integral. This allows writing the correlation functions in terms of conformal integrals coming from this, and interpreting the conformal integrals as a representation of the Mobius group in the space of regular functions in the Falter-McPherson model of the configuration space. We could recast this differential equation for the conformal integral to the toric GKZ systems. And on one hand, it is series solutions which appropriate domains of convergence, which matches with the existing results wherever they are there. And writing the invariant part of the conformal integral solves the GG system of equations. I didn't write down the GG system, but I wrote down the solution as an integral. It has an integral representation, allowing rewriting the bootstrap equation, predicting some bounds of conformal integrals for the toy models that we discussed. And with this, I bring this lecture to an end.
Thanks a lot. To the questions.
I couldn't talk from the plots. Are the bounds on the square measurement you're getting? Are they comparable to what you would get just doing numerics?
This I just evaluated this number. Okay, so if you're asking about the
Delta naught versus delta plot. But the delta,
I don't have enough expertise in checking this numerical stuff.
Yeah, but the way you plotted it, you're not solving our semi-definite problem.
No, I'm simply saying that if it crosses the unity, so sometimes it will be negative, so I'll have a bound from there.
Right.
So this I have not cross-checked whether this is a better bound or a worse bound compared to the numerical.
But this is already under the assumption that the scaling is
Right. So I have also not used the internal links. These are all scalars only. But it looks like that this can be useful in doing that. So now one can try to generalize this to with speed enough.
I got a bit confused. I mean, for the 4-point block, somehow it seems like one could just walk with the main block, and it should somehow match with whatever you have.
I see.
I mean, I'm sure that this is probably going to help more of the higher points.
That's what my hope is. Yeah, it does. So far, all I can say is it doesn't do completely useless. This implementation. So, and I have some leverage coming out of this GKZ system now.
You have time for more questions.
So, I really don't know anything about it, but what about the 3-point correlations, 0 or the Koushik block? Can you say something about 3-point?
Yeah.
I see. So they are
Conformal invariance covariance combinations.
So can we take, so you
See the problem that the thing is that the reason it is fixed is that here with 3 points you cannot write a cross section. It requires 4 points at least. So there's no ambiguity. The whole problem is in this ambiguity in fixing the cross ratio dependent part.
So you have some work with turbulence, that would apply this formalism for TP, but you tried, so it is.
I have not thought about it, but yeah, I mean it's possible to work. Yeah. the way you are presenting it.
So, Polygon did try for 2D hydro. And he got,
Polyakov knew about this design, so I guess it was possible he would have done it.
I don't know, you need to look at the.
Yeah, I've not studied that Polyakov,
He
that.
didn't get, by the way, he got, entropy K minus 3 is the correct result for the spectrum, the entropy cascade regime. He got 22 by 3, no, 22 by 7. There is not 3.
Yeah.
But all the deltas are there. Then
22 by 7 is like 5. So,
yeah, so the real answer is 3. I think. You believe 3, but he got 22.
he got 5 some. Yeah, I don't know. As I don't know that. But the Thunderbolt arguments in this language.
Okay, so let's close the session. Thanks.